Today we are going to be talking about the SN1 reaction, that is a nucleophilic substitution reaction that takes place in two steps. Up until now we've been talking about a single-step nucleophilic substitution reaction in which a nucleophile is attracted to a delta-positive carbon and there's a leaving group, usually a halide, that leaves taking its electrons with it. This gives us a transition state in which the nucleophile carbon bond is partially formed and the leaving group carbon bond is partially broken, and a final product in which the nucleophile is attached to the central carbon atom and the leaving group has left, taking its pair of electrons with it. Now suppose the carbon with the leaving group attached had some large groups on these other attachment points. It was quite large. And or suppose that the nucleophile itself was somewhat bulky. If either of these cases were true or both were true, that is, we had a large nucleophile and or a large substrate, this reaction would be incredibly slow, as the nucleophile would not be able to approach the opposite face of the carbon atom to give a one-step nucleophilic substitution. And this reaction, therefore, would not happen. So does that mean that the nucleophile and the substrate wouldn't react simply because of bulk? And the answer is yes, they'll react, but they will have to react by a different mechanism. In particular, the carbon leaving group bond would have to break first. This can happen from a bulky substrate, and in fact the bulky substrate itself will tend to encourage this to happen because it will alleviate some of the steric bulk around the central carbon atom. When that happens, we end up with an sp2 hybridized intermediate, carbocation, which has an empty p orbital. This carbocation is much less sterically hindered than the original substrate because the bulky groups are now in a single plane. After loss of the initial carbocation, it is much easier for the nucleophile to approach the intermediate, and in fact can do so from either side, to give one of two possible products. One in which the nucleophile replaces the leaving group from the opposite face from which it came in, and one in which the nucleophile has replaced the leaving group from the same face in which it left. These two outcomes give you two possible chiral isomers if you start with a chirality center where your leaving group was located. And this entire reaction takes a minimum of 2 steps. In step 1, the leaving group leaves. In step 2, the nucleophile makes a new bond with the carbocation. The reaction diagram for this reaction illustrates the 2 steps. In the first step, we have a very high activation energy to give an intermediate that is higher in energy than your start with, that is, the intermediate carbocation. In a second step, there's a relatively low activation energy process in which a bond is made from the carbocation and the nucleophile. It is net exothermic by a significant amount and is a fast step. Therefore, step 1 is the rate determining or slow step. And any factors that affect how easily the leaving group leaves will speed this reaction up. Most notably, the nucleophile is not involved in the reaction until the second step, which is fast, so that the identity and concentration of the nucleophile would have no effect on the rate of the SN1 reaction. Finally, a little information about what the SN1 means. The S in SN1 stands for substitution. The N in SN1 stands for nucleophilic, and the 1 stands for unimolecular. The reaction is unimolecular, involving only one molecule in the slow, rate-determining step. Only the substrate and its leaving group are actually involved in that process.